5.2, analyzing exponential functions. So let's look at this graph. We have y equals 2 to the power of x. So my base is 2, which means I have an increasing function. I have no x-intercepts because there are none. And I have a y-intercept of 1 because the value in front of my equation is nothing. I have an asymptote at y equals 0. And I have a domain of x such that x is an element of the real numbers. And I have a range that says that y is greater than 0. So that's kind of all the stuff you should be able to tell about an exponential before you even do anything with it. Let's make a table of values so that we're going to need it for the next question. So we got x, y, let's do -2, -1, 0, 1, and 2. So pause the video and I want you to figure this out. So you should have got 1 over 4, 1 over 2, 1, 2, and then 4. So our graph would look like this. So at -1/2, it's at 1/4. At -1, it's worth 0.5. At 0, it's worth 1. At 1, it's worth 2. And at 2, it's worth 4. So there is our graph. Now, just like in our previous units, we can apply changes to it. So we have y minus k equals c times a to the power of d, x minus h. And it's exactly the same as Unit 3, transforming functions. We just have a couple different letters now, and it's just in different locations. So for example 2, knowing that we just graphed y equals 2 to the power of x, and we had a function of x and y, -2, 1/4, -1, 1/2, 0, 1, 1, 2, 2, and 4. We're going to now graph with this transformations. So I'm going to make a table of values here, and I'm going to figure out what my c value is and what my d value is. I know that the d value is what affects my x, so I'm going to write it over here. And h also affects my x. And c affects my y. And k affects my y. So in this, my d value is, well, first of all, we're going to have to rewrite this equation. So y equals 3 bracket 2 to the power of, we're going to need to take out a -1, so this becomes -1 x minus 2. So because that negative is not in front of the brackets, we have to take out a -1. So our d value is -1, which makes our h value +2. My c value is 3, and we do not have a k value, so it is 0. So we're going to plug this into our new point, which is x over d plus h and cy plus k. So we're going to have x over -1, which is -x plus 2. And then to transform our y points, we're going to go 3 times y. So it's very similar to what we did in previous units. So where we have -2 makes it +2, plus 2 is 4. -1 times -1 is +1, plus 2 is 3. -0 plus 2 is 2. -1 plus 2 is 1, and -2 plus 2 is 0. So we've transformed those x points. We're going to multiply each of our y points by 3. So it'll become 3 over 4, 3 over 2, that's 0.75, and 1.5. And then 3, 2 times 1 is 3 is 6, 4 times 3 is 12. We also can check to make sure that our asymptote can be moved. So we have an asymptote at y equals 0, and timesing it by 3 does nothing, so it's still going to be at y equals 0. So let's graph this. So we have 4 and 0.75. So that would be like little. We have 3 and 1.5, 2 and 3, 1 and 6, 0 and 12, somewhere up here. Oh, wait. Alright, so it would go up and over. So there is our new graph. Our domain is still x is an element of the real numbers. Our range is still y is greater than 0. But it has just been transformed now. So you apply those transformations just like we did in Unit 3. Okay, using exponential equations for word problems. So the temperature of cooling water in a cup can be modeled by the equation T equals 89.726 times 0.972 to the power of m, where m is the number of minutes that have passed, and T is the temperature in degrees Celsius. So first part, determine the temperature after 52 minutes. So we're going to plug in 52 minutes. In for x. So go ahead, pause the video, and I want you to try typing that in. So the number you should have got was 20.49 something. So a little bit over 20 degrees. Very easy. What you might not know how to do, however, is solving for x when x is an exponent. So what is the time when the temperature is 51? So we're going to plug 51 in. And then what we're going to do is we're going to isolate this base. So to isolate the base, we're going to divide both sides by that value. And I'm going to leave it like that. So 51 over 89.726 equals 0.972 to the power of 52. And what I'm going to do from here is I'm going to take the log of both sides. So we're going to get into logarithms in the second half of this unit. But by taking the log of both sides, what I'm able to do is apply a rule that allows this exponent to be moved in front of the logarithm. So I have the log of 51 over 89.726 equals 52 times the log of 0.972. So you just learned your first logarithm rule. Anytime you have a log base whatever to the power of x, you can rewrite it as log x log b, or whatever words you want to use there. Okay, now we can get rid of, that shouldn't be a 52, it should be an x, because we're looking for x. Oh my gosh. That was from the last example. Okay, now we have an x. To get x by itself now, I would divide by log of 0.972. So I can do that to both sides. So what you should be typing into your calculator is this. And the number that you should get is 19.82 ... So a little bit, or almost 20 minutes it would take to get to 51 degrees. So let's do another example like that. For every meter below the surface of water, the light intensity is reduced by 2.5%, remaining at the depth. And there's the equation, 100.975 to the power of d. So first of all, I can tell that it's decreasing because the base is 0.975, which is less than 1. I can also tell you that there's no x-intercept, and that the y-intercept is at 100. Because this equation hasn't been manipulated very much, it's just been stretched out. I can also tell you that there's an asymptote at y equals 0. The domain is x is an element of the real numbers. And the range is y is greater than 0. And I could also do a quick sketch. It starts at 100 and it gets smaller. It is exponential decay. Okay, to the nearest percent, how much light remains at a depth of 10 meters? We're just going to plug d into B10. So 100 times 0.975 to the power of 10. The number you should get is 77.63. So that's percentage. Okay, now applying what we did from the last example. 50% of the light, how much is there going to be for the depth? So we have 50 equals 100, 0.975 to the power of d. We're going to isolate our base. So we have 0.5. This one I'm going to write as 0.5 because I can. It's a really easy decimal. Now I'm going to take the log of both sides. So I have the log of 0.5 equals d log of 0.975. Now I'm going to divide by the log of 0.975 to isolate our value of d. Pause this, type it into your calculator. You should get the depth to be 27.4 meters. Alright, that's how you solve exponential equations. See ya!